you, and I'm pleased to be here, and it is thankful for the kind invitation to this a mega event, I will say, in the domain of quantum matters. And the title of my talk is Frustrated Magnetism, Exotic States of Matter and Emergent Phenomena. See, when we talk about the frustrated, I think I should stand here, frustrated magnetism, there are various ways this frustration can come in spin systems. And if you can classify those areas, historically, it started with the so-called the spin glasses, and in early 1972 it was discovered, and then 70s and 80s a lot of work. And as you know, the gold iron, it is essentially you put magnetic impurity in conduction media, and then there is a lot of disorder. So basically the concentration is very, very low, and that is the way first very diluted magnetic atoms in conduction media, and the competing X interaction due to disorder, and this is one ways to get the frustration that we know. But there are many other ways, and in recent time, of course, geometrical frustration is one of the hot areas where the lattice geometry comes in, and in that case, depending upon how these moments, the spin moments are arranged, whether in a triangular lattice, Kagome lattice, or honeycomb lattice, for example, this is the 2D scenario, then there is geometrical frustration because it is related to the positioning of the magnetic atoms. There could be another scenario where there is exchange frustration. So there, the single atomic dipole moment is subjected to competing X interactions, could be positive or negative. So then these competing X interactions can give you the exchange frustration. So I will try to differentiate between these two. Quite often we get confused between these two. And the fourth type could be competing anisotropy. For example, in spin ice, so due to directional preference of spins, there could be frustration. So this is yet another category. So these four categories you can have when you talk about the frustration in magnetism. Now, how do you experimentally or even theoretically, how do you characterize, how do you know whether frustration is there or not, and to the extent of frustration? There are certain quick measurements, and of course this susceptibility, magnetic susceptibility, where this Q device temperature theta, and I'm sure that yesterday there was a session and all those things were discussed, so it is a continuation of that. Professor D.D. Sharma spoke in that session as a first speaker, and this index F, it gives what is called Ramirez frustration index scale with the Tn, and basically what it tells, see, if you look at this theta value, which I will tell in the next slide, it is like at this temperature the system should have ordered, and as per the mean field theory, these two should be same, but reality they need not be same, and that is why when this value is much greater than 1, then you call highly frustrated. Typically 10 or more F value is good number to say it is a frustrated spin system. Even experimentally could be observed at 50 in Kagome lattices. There is another way of looking at the existence of frustration in magnetic materials, to look at the anomalies in the specific heat. See, specific heat should show a peak wherever there is a magnetic phase transition and all, but if you see some deviation from that, then that could be yet another signature. And very important thing is called the residual anisotropy, entropy, which if it is large. And how do we measure this entropy? This is the specific heat, this is temperature, and I will give some examples. There you will see how residual entropy seen that in a frustrated system, that a large amount of residual entropy remains even if you cool the specimen down to near absolute zero. Now, when you measure this susceptibility, reciprocal of that, and as I said, this theta WC, Q device temperature, which you see it is proportional to the J. J is nothing but the exchange constant. So that means it tells that this is my exchange constant between the spins. So this is the measure of the strength. So then ideally when this J is able to overcome the KBT, it should go for the magnetic ordering. But if it does not happen, if it happens, then this and Tn, they are same, that is the mean field. But if that does not happen, that means something else is playing a role, and that is the frustration, and that's why this ratio is very, very important to measure whether this is really deviating from 1 in a very big way. As far the residual entropy is concerned, this is the entropy per spin, and as you know, if you cool the specimen and if you have come to almost zero temperature, but you see that still some entropy is left in the system, it has not been released. So this is called the residual entropy, and if this is high, that means that much entropy is available in the system, and that is due to this zero temperature quantum fluctuation. And this was, of course, this view graph taken from this famous paper. Yet another way the competition between moment can take place. Suppose you have a system where there is a magnetic order due to RK interaction, and this strength of this interaction between this 4f and conduction electron is measured by J. That is what J is plotted in the x-axis, and this is the thermal energy KBT T, and you see there are two terms. One is the magnetic order, that is the RK interaction strength is defined by this line, and this is the Kondo effect strength. Both places you have J. So beyond certain J value, that is at J equal to JC, you do not see any magnetic ordering. It gets destroyed. So this is yet another case, the famous phase diagram, that it tells due to the competition, the frustration between these two competing terms, the magnetic ordering is destroyed in a system. Now this is when we talk about the frustration, as I said, the lattice geometry comes into picture. Suppose if you have this kind of arrangement, the spins, moments are sitting at the three vertices and they are Ising type, that means they are restricted to align only one particular direction, and there is a negative X interaction, so they have to be antiparallel. And once this is antiparallel and this is also a negative X interaction, so this spin demands that this should be up, whereas this spin demands that this should be down, so this third one is frustrated. Of course, which third one you never know, so that is called the Ising, so that restriction. But of course, if you deal with Heisenberg or XY spin, because they can orient in space, here that is not allowed, but here it is allowed. So this kind of arrangement takes place in a triangular lattice. So this triangular lattice, so here it is a case, you see that I must tell you that X interaction is there, but this particular spin, it is frustrated due to its geometrical constraint. Because point to be see that X interaction between these two is negative, X interaction between these two also negative. So that means the frustrated spin is not subjected to two competing X interaction, one positive and one negative, which we normally say. That is not the case. So this is the real example of geometrical frustration, because there is no, due to positional constraint, there is no competing X interaction facing the frustrated spin. Whereas if you take a square lattice, here you will see that the frustration comes due to one individual spin gets two competing X interaction. One is positive, another negative. How it is? Let us say you have atoms, the moments are sitting, magnetic atoms are there in a square lattice vertices, and you have negative X interaction J1. So this is the spin alignment you get. It is very fine. There is no frustration. Now you take this square lattice and you switch on this diagonal X interaction, and diagonal is also now with this negative X interaction, this is your configuration. Now once you have also diagonal X interaction, that is the next nearest neighbor X interaction, this is the nearest neighbor, and that is also, let us say, negative, I mean antiferromagnetic, because these two guys are already parallel. These two guys are already parallel, and this demands, if it is antiferromagnetic, this demand these two should be antiparallel. So that means the E spin is getting subjected to both positive and negative X interaction. So this is the true example of the competing X interaction, both positive and negative. Unlike the triangular one, where there is no, the frustrated spin is not subjected to both positive and negative X interaction with equal strength. So this is the clarity I wanted to bring, and Hamiltonian goes like this, both the nearest neighbor and the next neighbor X interactions. But when there is a frustration, whatever be the origin, over and above, if you have some other ingredients, then that becomes very dangerous. Dangerous in the sense you get very, very strong quantum properties. For example, if you have geometrical frustration, over and above the system, the spin system which you are dealing with, it is a low dimensional system. That means not 3D, 2D or 1D or quasi 1D or quasi 2D. And your spin value of the magnetic atom is the lowest possible, that is spin half. So if you have these three all together, that means not only frustration but lowest spin and low dimensionality, then these are the ingredients for strong quantum fluctuations. So this is the dangerous combination in terms of the manifestation of the so-called frustration. And I will be giving some examples. Now, over the years, we have been working on several systems. So in this 25 minutes or remaining 20 minutes, I will be giving examples from our work, and because the time limitation, but of course you know the literature is very vast. So first I start with the triangular lattice. So how it is? This is the real system. This is a compound oxide material where this is magnetic atom. There are two cobalt sides. They form a Ising kind of chain because this is a ferromagnetically aligned. So ferromagnetic chains. By these three chains, they are forming triangular lattice. So that means in a planar structure, it is my triangle and there is a antiferromagnetic X interaction. Though along the line there is a ferromagnetic, but between chains antiferromagnetic. So what I just said, the triangular lattice, here it is a real system example, the how triangular arrangement is seen in a real material where with antiferromagnetic X interaction, and this third spin needs to be frustrated by this definition, and we have worked, and let me give one or two slides from this kind of work. So for example, when you say this kind of frustrated system with the triangular, what happens out of three spins, the one spin which at the one vertex of this triangle, it is not ordered. So this is called partially disordered antiferromagnetic structure. That is the structure. This is a disorder. This is totally disordered. And if you see this system, which you work with collaboration with Professor Sampath Kumar and others, and so their moment, nickel 2 plus subjected to have 2 Bohr magneton, rhodium 4 plus subjected to have 1 Bohr magneton, taking G equal to 1, but it is very, very less due to strong quantum fluctuations. This system, if you see the susceptibility, AC susceptibility with the frequency dependent, so you do see this kind of, and we have interpreted this as a frozen spin glass kind of thing. So the normal spin glass where you have both disorder and randomness, that causes freezing, but here the quantum effect is coming in, and from the inelastic Newton scattering study, what we see here that this excitations we see much beyond so-called this ordinary temperature, frozen spin glass temperature, which is around 20 K, here right up to 85 Kelvin. So this kind of new novel properties we see. Even one of our earlier studies, what we also saw that in the same series, same kind of structure, the magnetic ordering, of course, partially disordered antiferromagnetic Bragg peaks appears at low temperature, but above so-called the Tn, the formal Tn, we do see short-range magnetic correlation, and that is another hallmark of this frustrated system. So these are beautifully captured by doing Newton diffraction. We have subtracted the nuclear Bragg intensity, so only the magnetic intensity seen. So this is see the spin-spin correlation, so-called above the magnetic ordering temperature, means it is so-called in the paramagnetic state. So that true paramagnetism is not there in this case over the temperature scale. This is yet another relatively recent study by using this Spectra 3 resonant beamline X-ray resonance scattering. From that we could show that in this compound with the same triangular lattice structure that we cannot explain only with the dipole moment. See, whenever we talk about magnetic moments, it is understood that we are talking about magnetic dipole, right? Without saying that. So this is one example that we need to take higher order magnetic moment. Otherwise, this is my red curve, this is my experimental curve. So higher order magnetic moment presence is reflected in this resonance magnetic X-ray scattering in this fascinating triangular lattice system. Now let me move beyond that. This is yet another work again in a collaboration with Arvind Kumar Jogi. Bera is very much here, and in this case you see the triangular lattice again. So first I am completing the triangular lattice series, but that was uniform triangular lattice, but here you see the arms are not equal. See the bond length, of course non-magnetic atoms are there, oxygen there. So in this case the theoretical phase diagram depends upon J2 by J1, that is J2 is this one, by J1 this ratio, this is the quantum critical point, and on this system we have done careful neutron diffraction study, and what you see here again that of course at 2K you see magnetic ordering 3K, but as you increase the temperature, what you see the broad magnetic peak. So this is again, as I said, the very clear signature of so-called in the paramagnetic state, you see the spin-spin correlation is building up, and the good signature of this quantum properties in the spin system. If you go a little beyond, this is the fascinating way, the specific heat, magnetic specific heat, we have plotted here by correcting the lattice one, and what we do here as a function of temperature at different applied DC field, and this is my ordering temperature so-called Tn. When there is a zero field, we do have this specific heat peak at T equal to Tn, but when you increase the field, this peak disappears, and this is the corresponding phase diagram. The quantum critical point is evident here under the application field of 3 Tesla, and this is the quantum paramagnetic state. This is the field induced antiferromagnetic to quantum parameters through the quantum critical point. So this is what we could explain. Now, if you play with the triangles, so-called triangles, and as you know, if you make Kagome lattice, that is the picture of the Kagome lattice, and the one individual is shown here. So this is my building block which I already explained, and in that case, let me give yet another example. So here we have this copper magnetic atom, copper spin half, it forms the Kagome lattice. This is one Kagome lattice, this is another Kagome lattice. Interesting is that these two Kagome layers are separated by non-magnetic so-called BPE strips, and that separation is 13.3 angstrom. So that means you can expect that this system is effectively 2D magnetic Kagome layer, because magnetic exchange cannot propagate through this much distance through these non-magnetic ions. So this is what, and what you see here again this QD highest temperature minus 68 Kelvin, so quite large, but there is no magnetic ordering. So this is, as I said, very large. By the way, this sample was prepared in JNCSR Professor Tapas Maji's lab, and then when we do this magnetic entropy measurement, so this is my lattice part, this is my measured, and the magnetic part is this down to 86 millikelvin, which we did that time in Professor S.K. Dhar's TFR's lab, down to 86 millikelvin. And what you see here, down to 86 millikelvin, first of all, we do not see any magnetic phase transition, and what you also see, the 88% entropy of this copper spin is released down to 86 millikelvin, but there is no phase transition, magnetic phase transition, and putting in other way, only 12% entropy is left to have any phase transition if it is feasible below 86 millikelvin, and that is which is very, very unlikely, because 12% entropy cannot lead to yet another magnetic phase transition. So this kind of residual entropy living at this kind of very, very low temperature is a clear-cut signature of this 0 point quantum fluctuation and quantum properties of this kind of fascinating system, and very large theta value without Tn. So here if you define the F factor, it is infinity, because T, no ordering. So or even if you put it is 86 for argument's sake, then you see what is the value of that F factor.
Professor Yusuf,
yeah,
you have 5 minutes.
Oh, so time is really okay. So then I'll be going little first. So this is the Newton diffraction, confirms that there is no magnetic ordering. This is the phase diagram. This is the spin liquid under magnetic field. We do see this transition from spin liquid to ferromagnetic in this system. If we go yet another example, maple lattice, that is again playing with the triangles. In this case, which we worked recently, Anup Bera is here, and in this case again we see that magnetic short range correlation much above the so-called ordering temperature, and this is the this is the 2D plot that how this diffuse magnetic scattering is there. If there is a sharp Bragg peak, then these will be dots, So it is a H-scale plane, we have mapped it, how the magnetic correlation is there. Now I move to from triangle to square lattice. In square lattice we have worked a lot, and this is the theoretical phase diagram. Depending upon J2 by J1, one can have spin liquid over this theoretical paper they published. And then this is one system we work where the copper square lattice, and there is a both J1 and J2, and here again this is the separation between two magnetic lattices. So copper forms the square lattice here in this system, and this is the magnetic structure, but message is that copper spin, what we measure, it comes only 0.79 Bohr magneto. Theoretically, when the quantum fluctuation gives 0.6, so it is very close to that. So that means this 1 Bohr magneto is reduced to this kind of value due to quantum fluctuation of this square lattice of this copper spin half. Then yet another system, that is the trimer system, but here I will not speak more. Here I want to say only one part. This was done in collaboration with the Manoranjan, Anup Bera and others. So here I want to speak about only one part, that is J3. There is a spin trimer between two end spins, J3, how J3 gives the magnetic frustration. So then only frustration part I want to talk about that. And in this system, you see the magnetization, quantum 1/3 magnetization Plato, experimentally and theoretically supported. But what we have, and specifically also it is shown here. So what is important to note here, that J3 by J1, that is this N2 spins, when they interact, that gives the frustration, and beyond certain strength, this so-called the low magnetic field state, this is so-called this state, low magnetic field state disappears. So this is the effect of this frustration in this quantum entangled spin system showing 1/3 magnetization Plato. Then we have extended the work. This is one of my PhD students did. If you have the mixed trimer and dimer system, how you can play with that? Previous one was just trimer system, but it's a mixed one. And in this case, we can play with this so-called this quantum magnetization Plato. And if this is a uniform type, all are same. It is like a uniform chain, uniform magnetic chain. So not interesting enough. But we can have this 1/3 magnetization Plato. We can have not 1/3, 1/5 magnetization Plato, 3/5 magnetization Plato, depending upon this J3, between dimer, what is the exchange constant strength. So one can design this kind of novel system, and there is a possibility that experimentally we will be able to verify this. This is for the last example. This is the honeycomb lattice, where we have shown that both Kitev and Heisenberg model, because as per our Newton diffraction work, this magnetic structure is the zigzag one, and that falls in this phase diagram. So if it is, see, this is the phase diagram, this is the J and this is the K. K is the Kitev term and J is the Heisenberg extent. If it is purely Kitev, then J is not there. See, this is the theory developed with respect to mixed Heisenberg and Kitev combination, and our system falls in this domain. So there is finite Kitev term. And in this case, by doing magnetization on a single crystal along different field direction, so when field is H parallel to A star, what we could see the quantum spin liquid which is coexisting with the canted antiferromagnetic state over this field range. So this kind of phase diagram came out by doing this kind of study. And it was extended by doing this high field terahertz spectroscopy, where continuum scattering we could see in collaboration with Professor Wang, and this is a very novel technique, in fact, to look at the quantum correlations.
So, Professor,
Yeah.
we are now in question time.
Yes. So let me summarize that in my talk, what I presented, that there are different kinds of lattices, either 1D or 2D, and 1D I gave example timer, mixed timer and dimer, and in frustrated system, whether square lattice, whether honeycomb, whether kagome, whether made of triangular and maple lake, various examples, very fascinating physics comes. And as I said, when this frustration along with the low spin value, along with the low dimensionality, these are three are very dangerous good combination to see the quantum properties which are manifested even at very high temperature, even as high as very close to room temperature. Thank you so much.
Thank you for the nice talk. Questions?
Thanks for again fascinating set of data. I just wanted to comment about your last thing about this Kitev-Heisenberg model. There is a theoretical work by Tanmay Das and Yogendra and myself about an intermediate intrinsic glass tail. So I can talk to you because it's a very clear prediction about from numerics we are fascinated.
Okay.
There's a tendency for it to become a quantum glass.
Yes, yes.
Even without disorder. You can check.
Okay, we'll have more discussion. Thank you so much. Yeah.
Okay, so thank you very much for your talk. I have just a general understanding question. In the system, you saw the calcium cobalt V207. There you showed on the basis of your neutron scattering and the heat capacity data, there's a quantum critical point, right? But in general, for our general understanding, we know that to justify a quantum critical point, you have to justify the quantum fluctuations.
Right.
Yeah? So in general, this usually comes from some kind of many other microscopic measurements. Yeah. Do you have any other evidence there?
Yeah, it's a good point, and that is what is expertise. We must be showing you in near future the inelastic neutron scattering data on single crystals of that compound. See, the bottleneck of all these things, we need to grow large single crystal, then only, but that is definitely the requirement, and we will be definitely showing you one day the inelastic neutron scattering data on that system down to very low temperature. Thank you for raising the point.
Okay, so there is very nice talk, and this is regarding this cobaltate. See, usually in D5 systems, right, it's Heisenberg term marks the Kitaev term, and it's very difficult to basically find the spin liquid state. But on the contrary, find for this D7 system,
Right.
you do see a spin
Yes.
liquid in the phase diagram.
Yeah.
So, any understanding how the Heisenberg term is weakened, or
See, you are talking about
sodium, cobalt, tellurium oxide?
yeah. So because in that case, yes, this is a point. What we have shown here, that actually we have done inelastic neutron scattering data, which I did not present. So there we have shown the magnetic transitions, and we have established that indeed the ground state of for cobalt is J effective equal to half. So due to spin orbit coupling. So this is one important point, that can we have this kind of feature in 3D system, and this is the experimental confirmation that indeed in this 3D system of cobalt we could have J effective half, not by spin but by spin orbit coupling. And if J effective half is the ground state, then what kind of magnetic excitation we expect, and we have got those transition lines which I did not present. But I have the slide maybe somewhere, Thank you for that.
In your compound CaCO B2O7, you have constructed the phase diagram. So in your phase diagram, in continuation of earlier question, you have shown that quantum critical point. So from isothermal magnetic measurement or specific heat measurements, have you calculated the quantum critical exponents to specify that it is quantum critical point? And my second question is that about that it is you have said that quantum paramagnet. So why not it is fully polarized state or just a classical paramagnet state or correlated state?
That is a very naive question. As you say, when you say correlated system, how do you distinguish whether it is the classical correlation or quantum correlation? Because in this case, what we see, there are n number of features which help us to say it is quantum in nature, because the correlations nature, yet in this case, we have done the Newton diffraction, and from that we see the nature of correlation is definitely much away from, obviously not paramagnet, even much away from the field induced so-called the interaction, spin-spin correlation, short range correlation, much away from that. So this is a very long and good paper. I mean, you may kindly see that. Lot of evidence is there to say this is indeed quantum paramagnet, not the classical paramagnet, not that short range correlated classical, quote unquote, classical paramagnet.
Okay. Thanks for the answer. In the interest of time, let's close the talk.
Thank you.